Well, let's go ahead and get started. This is chapter 8, program modules. Now, your program consists of a list of instructions, and we might have branches in there, looping based upon the branches, but it can become kind of cumbersome with all the different lines of code you might have. So what you can do is you can modularize it. So you can put certain pieces of code in certain locations. Example of that. And this is not an assembly language example, but I think you get the idea. If we're dealing with polynomials, specifically quadratics. So something like ax squared plus bx plus c. Well, things you can do with it. You can find the zeros. You could factor it. You could find the vertex. You could find the axis symmetry. Or find the min or max. Find the y-intercept. So these are different items you could do. Well, these would be a logical breakdown of zeros, factor, vertex, axis symmetry, min or max, and y-intercept. And so within our program, if we were finding all these items, we'd break it down into modules. Each one of these would be a separate module. So that's the idea. It's on page 98. It says Chapter 2 stated that a well-designed program should be built of small modules. If you have too many lines of code in one particular module, it becomes kind of cumbersome, kind of hard to follow. It says, as the amount of text readily viewed is about 1 page of normal TypeScript, the guideline is that the program text of a module should not exceed this. And then it says, goes down further, says that including all comments and headings, you should have no more than 40 to 50 lines. Now, you can plug them all into one big program, not use modules, subroutines, but then that becomes kind of hard to work with. And this gives you an example of breaking it up. I'll put the instructions, ask for the first input number, obtain a valid first number, ask for the second number, obtain it, add these numbers, display a message stating the result is, display the result of the addition at the end. And again, each one of these, if you did an assembly language, would be huge. So, or large, I shouldn't say huge. Now, one way to break it up is to use subroutines. And see, it says the most common but not the only module form in assembly language program is a subroutine. So what your program will do is it'll call that subroutine and then it'll return from where it's called from. And it shows you an example of that Over here we have our subroutine. Here we have our main program. So this calls a subroutine, comes down here, runs this line of code, does that return, and then returns to the next line after that. But you can call a subroutine in multiple places. So I'd call it down here, and I would call it there. And when it did the return, it returned from here. And so part of this is going to be able to determine where do we need to return to. Grab a drink here. Because if it's a RISC structure, the ARM instructions for subroutine call and return perform fewer actions than similar instructions of CISC type CPUs. Consequently, the ARM program has to perform more tasks than a CISC program when creating a subroutine. The ARM subroutine call instruction is branch with link, mnemonic BL. As opposed to all the conditional, as usual, all the conditional forms are allowed. Now, branch with link performs all the actions of a normal branch. It also puts the address and instruction that immediately follows the branch with link instruction into register R14. Well, let's take a look at that. Okay, I've got a program here. I'm going to run it. Okay, so I'm sitting right here. This is my start. Actually, I guess I need to restart it. So stop. Start it again. I do a debug run. And this is one I copied out of the ARM manual online. It's not out of the book. The one out of the book didn't work for me. So obviously got some kind of configuration settings that are different. Okay, so this one's just moving 10 to R0. And we see A is in R0, so I move 10 to it. X. Then I move 3 to R1, and I see R1 has 3 in it. Now here's our branch that we're talking about. And it's going to go down to this do add. So if I run that one. Now, by the way, notice that the R14 is now 0x and then all Fs. This indicates to you that you haven't branched. Now, if I branch, comes down to here to my subroutine, and it'll perform the code here. But notice that R14 now has 16D in it. And if I come up here, although it's not real easy to see here, here's my 16C, and that's where it's going to return to. That's all. It's weird to me because it's one greater. See, it's 16D, but it's going to actually run this move statement when it's done. So if I keep going, it does this add. It adds A plus 3, 10. A is 10, so 10 plus 3 is 13. And see, A, B, C, D, 10, 11, 12, 13. So that's D. Now notice that my my register 14 is still 16D. This branch here, this is going to be based upon the where it's called from. And so it'll use this LR right here. And you see that I got that here. I got LR. It'll use that to figure out where to go back to. So that's how it keeps track of where it came from. And if I do that, then I'm back to here. And again, it just seems totally strange to me because you see in register 15, it says I'm at 16C. Up here, it says I'm at 16C. But 16D is what told it where to go back to. So it's like one greater is what it appears like. Okay, and this is going to move 18 to R0. And that'll move that number in hex to R1. And that's actually the, well, no, I did that again. And then branch. So really, I should have had another go-to here. That's curious. Unless their example was meant to loop infinitely, but then going down doing that code inside that subroutine wouldn't make any sense. I think it was just an error in the code I got. Okay, well, let's change this then. Come down here, I'll call it done. And then here, I'm going to branch to done. So let's build target. And run it. Okay, so right here, there does that branches to do add. Does that, branches back, or returns back, I should say. And then branch to done, which is after that. Okay. So then, this is again talking about how R14 is the link register. The assembler accepts the names LR, uppercase LR, R14, and uppercase R14. Let's see if that's true. Not everything in this book is true for what we're working with. Okay, so let's try that. Okay, and then run that. And okay. Okay, I guess it did work. But again, that keeps track of your where you need to return to, where it's called from. Let's see. This return from subroutine is one of very few special cases where the programmer changes the contents of the program counter by moving a new value directly into it instead of using a branch instruction. Such explicit loading of the program counter is not necessary for most the processors. Okay. When they do it here in their example, it's a little bit different than what we're having to do. Because we can access it with just using the LR. We're not having to actually move it. It keeps track of it for us. Constructing subroutines using branch with link is straightforward, but a problem arises if the code of one subroutine includes a call to another subroutine, a process called nesting of subroutines. Section 8.3 illustrates a main program calling two subroutines, with the first subroutine also calling a second. This only has two levels of nesting, whereas many more levels of nesting are common. Figure 8.3, the second subroutine is called by the first. If the first subroutine return address is an R14, when the second subroutine is called, return address for the first is lost. Is replaced by the return address for the second. Most CISC type CPUs automatically save return address in memory instead of registers. This area memory used for return addresses is operated as a last in, first out LIFO store. When it holds return addresses and related items, it is a program stack. Another description of the store is that is a push in or push down and pop out or pop up memory. Each item, when added, pushes the previous ones more deeply in memory, and each retriever causes remaining items to rise upwards. Well, what's that mean? Means that when we get down here and we're ready to go back, you can only have one value in register 14. So that's what it's talking about, handling that differently, where you're putting in a stack where you're kind of pushing it down. It's like a stack of plates at a restaurant. They come and they put a buffet. They put the plates on there and push it down, and so the one on top is the first one that comes off. And so when you're calling subroutines, the last one called will be on top, and so it'll pull that address. Here's an example of that. We got our main program. Here's our subroutine 1, so it calls that, and within subroutine 1, it's calling subroutine 2. And when it gets ready to do the return from that, has to return back to here. And so when this is done, it needs a return to go back to here. But if we just had that one register, then this would wipe out the return here. You see, then we got a return here back to this, since I can call subroutine 2 directly. Large programs contain many subroutines and many levels of nesting. A stack is essential for storing return addresses and other items. A RISC processor cannot perform several memory accesses when executing one instruction, so BL cannot store the return address in memory at the same time as it performs a memory read to fetch the code of the first instruction of that subroutine. Link register is a temporary store for a return address. It is the program's responsibility to copy return address from the temporary position in the link register into the stack memory. Therefore, when seeing ARM assembly language, the programmer must set up and manage storage and retrieval of return addresses using the stack. However, ARM defined a standard method to be used. Always use this standard so that other features operate correctly. And the ARM instruction set includes features which help in stack use, provided the standard method of creating and using subroutines is followed. Stack must be created as a LIFO memory within a normal processor system memory address space. Standard method for an ARM system is to use R13 as a stack pointer. See the R13 here? The SP is our stack pointer. Okay. The assembler allows SP or SP to be used instead of R13 or uppercase R13. For exercises, the setting depends on environment system and target system specified in development system settings, where the first instruction of any program is to load the stack pointer. Although we haven't looked at it very close, we haven't needed to. These other four files, are performing some of that for us, so we don't have to worry about it. Couldn't tell you where it's at in these files, but that's what they're referring to. For early exercises using the Kyle tools with the real view assembler and development system settings suggested in Appendix 3, stack should be set to this value. Hard wouldn't set to that. This value is because LPC 2102 is set as the actual hardware device. To set stack to this, the following line should be included as soon as possible after the label reset handler. So we've got our LDR and we'll load it in an SP. To hear the BXLR, we know that's a return from a subroutine. User initialized stack heap. I was trying to locate if there's any other special ones kind of put in there. That's a huge file. But anyway, that's these last ones we're not supposed to actually touch, are being allowing us to branch and allow us to keep track of the stack. Using an earlier ARM development tools such as ARMulator or Valuator-7T sets initial stack address to a different value. Okay. Storage of subroutine. Storage of subroutine, return address is an important function of stack. Another is storage of copies of register contents when they're changed by the subroutine. You'll find that sometimes when you're writing a program, you'll be writing items to the stack and not even realize it with a higher level of programming language. You see this with recursion, and it'll run out of memory. That's one of the problems with recursion is you can have issues like that. And again, the message you see refers to that problem. I don't know if I could create one of those issues or not. Probably not, but let me see. Okay, so public int, call it I. If I don't need to return something. Let's try that. Oh, a red squiggly under it. What doesn't it like? Object reference. There it is. Process is terminated due to stack overflow exception. You'll see this in programming, and you're sitting there scratching your head. It's like, well, why is that occurring? Well, that's occurring because in this case, I'm just infinitely calling itself over and over. So it's sitting there pushing stuff back on onto the stack. Eventually, it overloads the stack in terms of memory, and you get that error. Okay. Let's see. Now there's storage copies of register contents when initiated by a subroutine. In most subroutines, the programmer uses registers to hold temporary values, local variables, which are only required within a subroutine are discarded on return. A program that calls a routine may be used by many registers for its own local variables, which should not be changed. For large programs with many levels of subroutine nesting, it is difficult to determine which registers must not be changed. A simple method is to avoid problems is to save all registers and used on a subroutine on the stack, which means that I would take those values that I have in my program that I've been manipulating on the register, and before I call the subroutine, I would push those on the stack. Um, Except for very simple subroutines that do not call other subroutines, contents of the link registers must be stored on the stack near the start of a subroutine must be restored to the program counter by the return process. It may also be necessary to save the contents of other registers to prevent their loss. Values could be saved using multiple STR and LDR instructions. This is cumbersome and requires that the programmer correctly changes the stack pointer. 2ARM instructions perform stack operations efficiently, store multiple STM, copies the contents of multiple registers to the stack, and load multiple LDM. Reverses the process. STM and LDM. STM over here, you see that we're storing off R7 and LR. I think LR was R14, I think. Here's LDM. We're bringing back R7 and PC. So again, you're pushing it down and popping it off the stack. I haven't tried this. Some of the code they have works, some doesn't on this, so we'll see if this one does. Okay, so before I branch, I'm going to put that on the stack. And it tells us to do and actually they do this within the subroutine. And we're going to store off. We're going to store off. It keeps going back. We're going to store off R0, R1, and LR. And here I'm going to load it back. R0, R1, and LR. Okay, so I'm right there. Branch down to here. And R0. Do that. That gives me D. Oh, I wanted to screw those up. But I suppose if I do it now, it should go back to A. Let's see. It does. So it returned it back to A. So this stored off our values. Then we made this change, and then this put it back, which isn't actually what we wanted here, but that's how, if you're in a subroutine, you can do the store to store off the old values, do whatever changes you need to, and then restore it to get those old values back. This talks about the example we had here with the FD. Let's see. Stacks are operated so that stack pointer automatically moves in the correct manner as items are stored and retrieved. Usually the action to store something in the stack is called a push and retrieval is a pop. So this stored all of our values. Now realize that a stack you can, let's see. Store R0, R1, LR again. And here I'm going to change. I'll put an E in there. Store it off again. That makes some changes. And another load here. Okay. Okay. One error. That's not good. Doesn't like the 1, 2, 3. Let's just put C in there. 2 errors. Got worse. Bad symbol C, not defined or external. Oh, this has to be decimal. What am I doing? The 0x is when it's okay, so that do 12, which should be C. Okay, so now let's try it. Okay, so I'm right here. Run that. I'm going to do my branch. So go to do add. I'm right here. And what's an R0 now? R0 is currently an A. So run that. I put a C in there. Now I'm going to push that on the stack, these items. Now it doesn't have to be 3. You could put 8 items on the stack. However many you're trying to store off there. Okay, so R0, let's see. Okay, so I'm down there. And R1, I'll push 11 on, which is B. Push that on the stack. Gonna add those. That wipes out R0. There's one of our loads, and you see it puts one of them back. And then this puts the other one back. So again, that's how you, these are our pushes, the STMFD, and our pops are the LDMFD. Talking about the ascending and descending, nothing too exciting there. D indicates descending. Subroutine construction. List of registers which must include LR, so you have to have LR there. It's probably exciting stuff on the first pages. So we get down to here, our example code, and it doesn't work exactly as we type it in. You see the idea. So up here, I'm declaring number of values equal to 5. So number of items in the list. Got our standard here. This. Get down to here. We're initializing the stack pointer. So remember SP is our stack pointer, and that would be register something. SP is register 13. So that's loading a memory address onto it. So that's where we're going to push. When we do our stack, that's where it's going to go. Here we're going to move the number of values. So come up here, gets the number of values. Oh, there it is. Which is 5. So it loads 5 in R3. Move 0 to R4. Then we got our load And in register 5, we got our data start, which is down. Clear down to the bottom. And that reserves 20 bytes of memory for the data. Set pointer to the start of the data, start of the addition. Okay, so we're looping here. And so we're going to get the value at the pointer, advance the point. Then add the value just obtained to the total. Okay, R4 is our total because we put 0 into it. Okay, I see what it's doing now. Then we wait to slow the program. So come down to the delay down here. Believe it or not, there's some issues with hardware. Is the speed of it, and it used to be a API call that you could run that would slow down the program. It didn't used to be that these programs talked as seamlessly as they do now. So sometimes you would issue a call to a third-party program, and you're waiting for some results to come back. And as a result, in your own program, you have to delay. You have to wait and give it time to process. Now it looks like what this is doing. So it comes down here, here's my branching, goes through, stores off my values in my register, so pushes them. And then down here, my LDMFD pops them. Okay, using R7 as a delay counter, decremented by 1. Yeah, decremented by 1. And it'll keep looping. Where branch not equal weight, go up here to the weight. So keep going through, subtracting 1. So it's creating a loop. Really doesn't accomplish anything except for slow delays. Let me get up just for a minute. I need to stretch my legs every now and then. I get sitting too long. Unfortunately, showing you examples out of the book and typing some in the computer doesn't give me that opportunity. Okay, talked about this. Now our stack form. ARM has unusual features that the programmer decides if stack has an ascending or descending structure. It also allows the use of the full or empty option. Therefore, stacks may be created with 4 different forms. However, the use of STMFD and LDMFD is so widespread it should be the only one used. ARM encourages so strongly that the UAL introduces mnemonics push and pop as alternatives. So instead of putting that at STMFD and LDMFD, use push and pop. I don't use any of the programs, but they talk about it. Okay, so we got our push condition, pop condition, then our registered list follows that. And again, that's in place of our LDMFD and STMFD. Note that these forms do not specify the register uses a stack pointer. They always use R13. Our program over here, we did not refer to R13 directly, but we referred to the stack pointer. And it says readers use an assembler, which sports use push and pop, or advise use those forms. Here it's talking about passing information to it. Again, you can use the stack to do that. So you can push items on there. So anything we have stored doesn't have to be like a program counter or anything, or LR. Anything we have stored in a register, we can push down on the stack. There's a number of values equal to 5. Come down here. We're initializing the stack pointer, so where it's going to start at. Number of values goes to R3, 0 goes to R4, and then our start of our data down here. This sets point to the start of the data. Get value at the pointer, advance the point. Add a value just obtained to the total. Select delay amount. Delay to slow the program. And decrement the count and set flags. And loop if not done required times, and no operation to help testing. Now this this flow chart we have here goes along with this program on the next page. Here we save our environment, preserve necessary register contents, if necessary, by pushing them onto the stack. Set our error equals 0. If divisor is equal to 0, true, then you come here. False, come here. If divisor is equal to 0, you can't divide by 0. You set your error equal to 1. Then end if. Restore environment and return. If it's not equal to 1, I'm over here, that's false. You set the quotient equal to 0. Increment quotient. Quotient is equal to quotient plus 1. Subtract divisor from dividend. Repeat until borrow occurs. Add the divisor to the dividend and decrement the quotient by 1. So over here, we're pushing it on our stack. This is assuming that it's set up your stack correctly in terms of memory location. Moving 0 to R2, R1 to R1, and branch if it's not equal to the not division by 0. And if you do, you move 0 to R4 and go through here. Otherwise, Okay, so branch not equal, so not a division by 0, comes here and does this line and then it keeps on going. Maybe missing it, but I'm not seeing where it's branching back. Probably looking right at it. I don't think it's branching back. Talks about subroutine testing. We've been looking at that. Here's an example of stack behavior. I don't think there's a flow chart that goes with it. Well, stack contents as program 8.3 executes. Okay, that's 8.3. Program 8.4 got 2 subroutines. Okay, we're initializing our stack. I really like to know where that's at in those code files. Here's test point 1. Branches to sub 1. Here's sub 1. Here's sub 1. Stores off the stack and register information. Here's S1.1. Branches to sub 2. Which is down here. Stores off the stack information. Does whatever. Then retrieves it. Looks like this, this is just a framework. As you get down to here, there's no subroutine actions. So just the general idea of how a program should go. And there we go. More advanced topics. Nothing really there. It's kind of all I really wanted to show you out of that. That subroutine. Now, the main item for this week is going to build upon what we covered before spring break. So hopefully you've had time to look at those examples and work with it and so forth. And I'm going to have a test out there for you. Now, the test is based upon an if statement. And then also it refers to a looping construct, for and a while. And we talked about some examples of that. And pretty much for programming purposes in assembler, what I'm looking for, you can just use your standard branching to achieve those. The project is not, well, it's not a project, it's a test. When you go on Blackboard for a week, you're going to see it. It's a timed test. Assembler's a little bit trickier to work, so I'll probably increase the time on that a little bit. But pay attention to the time before you start. I'm probably going to push it out to 2 hours. And there's 3 questions it'll ask you. They're essay form. Each one's worth 60 points. And what you'll do is you copy your code and put it in there, and then what you found out for your answer. It could be what you find out for your answer isn't something that is displayed directly. It's something that you look at in a register, and you see what it's equal to. This is a part of our accreditation. So this is how we assess program level outcomes. So if you're wondering, I don't give a lot of tests, just forced to in this case, because I have to have some way to measure how people are doing in the program. So anyway, I expect that'll probably keep you challenged. Make sure before you take the test that you review the compare that we looked at, and also the looping construct we looked at, especially the video from last time. If you watch that entire video, that's going to probably be your best one to take a look at. And we'll go ahead and stop the recording here.